Good evening, ADAS. A pleasure to be back here to tell you this time about It's Not Rocket Science. From the subtitle, perhaps you can see, well, yes, it is rocket science, but I'm going to try and convince you that it's really not that hard as long as you skip the maths.
What do you do?
Well, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science.
Rocket science is thought to be hard, and we're going to see whether or not that's the case this evening. I am not talking about how you build one of these things. If you want to build yourself a Saturn V in your back garden, go get the Haynes manual, which tells you how to do it. This is not about how you build rockets. It's about how we use rockets to get from one part of the solar system to another. So I'll be discussing what rockets are for, if you like. We'll be looking at different types of orbit. We'll be discussing how to go from A to B, in other words, how to go from the Earth's orbit to the orbits of other planets. And then I'll finish with looking at Lagrange points, these parking places where you can park a spacecraft like Gaia or the James Webb Space Telescope, for instance. So firstly, rocket science in terms of, well, what does a rocket actually do? If you ask a lot of people, what's the primary function of a rocket? Quite a number of people will say, well, the prime function of a rocket is to get you up above the atmosphere. Well, strictly speaking, no, that's not the prime function of a rocket. It's not to lift you above the atmosphere because when you think about it, the International Space Station and the Hubble Space Telescope, they are still in the atmosphere. Yes, it's rather rarefied up there at 500 kilometers altitude, but it's still within the atmosphere. What you need if you want to go into orbit around the Earth, or what you need in order to escape from the Earth, is horizontal speed. It doesn't matter, in a sense, how high you go. Yeah, it's not a bad idea if you get above the atmosphere, because that produces a bit of friction, but it's not, strictly speaking, the height that matters. It's the horizontal speed, and that's what rockets are designed for. We've known that for hundreds of years. Back in the 1686, Newton wrote in the Principia that if you fire a cannonball, well, if you don't fire it very fast, it'll land some distance away. But if you fire it fast enough, if you have enough horizontal velocity, you can go in orbit around the Earth. And that's why we have rockets. So yes, rockets go vertically upwards to start with. But if you watch a rocket launch, you realize it's not long before they start tilting over. That's not a mistake in terms of the perspective of the camera. That's what the Saturn V is actually doing. After a little while, it starts to lean over to build up horizontal velocity, because that's what you need to go in orbit around the Earth and then ultimately to escape the Earth. If you don't have horizontal velocity, if you just have a rocket that goes up, you end up with something like Blue Origin, which basically goes up, and once you're done going up, what happens? You fall straight back down again. If you don't have horizontal velocity, you can't go into orbit. So New Shepard, for instance, went to something like 100 kilometers altitude, but after 10 minutes, it was back down on Earth again. Horizontal is all important. So let's think about orbits and how we actually go into orbit around the Earth and how ultimately we want to go into orbits around other parts of the solar system. The definition of an orbit is simply the path of an object which is affected only by gravity. In other words, if you're under propulsion and you're affected by gravity and the force, the thrust of a rocket, then technically you're not in orbit. As soon as you're coasting only under the influence of gravity, then you're in orbit. So we tend to think of orbits of the planets around the sun and possibly the orbits of moons around planets, etc. Kepler first observed that the planets appear to orbit in ellipses, and Newton figured out why, the universal law of gravitation. Newton figured out that the orbits of planets follow one of the so-called conic sections. If we take a cone and slice through the cone horizontally, we get a circle. If we slice at an angle, we get an ellipse. If we slice at an angle parallel to one of the sides of the cone, we get a parabola, and if we slice at a more jaunty angle, we get a hyperbola. In other words, these 4 different so-called conic sections are all variations of how we slice through a cone. If we plot them out slightly differently and show how they all have a similar focus, the middle of a circle or one of the 2 foci of an ellipse, when we think about the shapes that orbits can take, circles, ellipses, parabola, hyperbola, they're the same shapes as we use to make mirrors in telescopes. We can make mirrors using, effectively, if you think of the 2-dimensional equivalent of a 3-dimensional sphere, we can use circles, we can use ellipses, we can use parabolas, we can use hyperbole to make mirrors. The reasons orbits are the same shape as mirrors in telescopes is basically because the maths is the same in both cases. So we know that planets follow closed elliptical orbits. Such a few examples are shown, something that's nearly circular and ellipses of different eccentricities. If an object is coming in from way out in the Oort cloud, a huge distance away from the sun, then it will follow an orbit very close to a parabola. So a parabola is, in a sense, an ellipse that's been stretched enormously. And you could say a parabola is the ultimate limit of stretching an ellipse until it's infinitely long. If any object comes into the solar system not by dropping in from the Oort cloud, but by coming into the solar system at speed, then it will follow a hyperbolic orbit. And we've seen that a few times. So for instance, in 2017, this rock came into the solar system in 2017, and it came in and it followed a path, and we can either trace its trajectory to see what its path is, turns out to be a parabola, or we can simply measure how fast is it going at any given point. If it's going at greater than the escape velocity of the solar system, we know it's going to escape the solar system, and we can work out from symmetry it must have come in at the equivalent of escape velocity. So simply by following the path of an object, we can figure out how is it moving around the sun, or is it an interloper that's come from beyond our solar system? As far as understanding orbital mechanics is concerned, yes, there's a bit of maths there, but I argue that you can boil it down to a very simple set of observations. So let's imagine we have 2 hypothetical planets here going around the sun. The green planet is closer to the sun, so it feels a stronger gravitational pull. And so it goes faster than the red planet, which is further from the sun, and hence the red planet feels a weaker gravitational pull from the sun, and hence moves more slowly. Let me just run that again, because this is crucial. Closer to the sun means you move faster. Further from the sun, which means you move slower. It's not simply that the red has got a bigger racetrack to go around, it's moving at a slower velocity in terms of how many kilometers per second. So its year for an outer planet is much longer than the year for an inner planet. That's rather important, so we'll see this particular animation again in a short while. We can see what's going on, for instance, around the sun. I know there's a lot going on here, but effectively we have objects in low Earth orbit going around the Earth in about 90 minutes. Satellites at much greater distance, like GPS satellites, go around the Earth in about 12 hours. And if you're out here in geostationary orbit, you're going around the Earth once in 24 hours at the same rate at which the Earth turns. The closer you are to the Earth, the faster you go, the shorter your orbital period. No different from objects going around the sun. But it may come as a surprise to realize that whenever we have one object going around another, one planet orbiting the sun or one moon orbiting a planet, we can calculate, as it were, precisely, if we ignore everything else, we can calculate precisely what's going on. The 2-body problem is soluble. But amazingly enough, the 3-body problem is insoluble. If we've got one object going around another object, which is itself going around a third object, we cannot calculate for any arbitrary setup how that works. Newton has told us exactly how to solve the 2-body problem. The 3-body problem can only be worked out approximately or with numerical simulations. So for instance, we can start with something that looks soluble. What if we've got 3 objects orbiting in what appear to be ellipses? Everything looks fine, but if we run the simulation a bit longer, we realize actually they're not doing quite what we thought they were doing. Because after a little while, we realize, yeah, it looked like they were in nice, sensible elliptical paths, but actually it's a chaotic system. We do not know how to solve that. We can only solve the three-body problem in very limited set of circumstances where we know exactly where the three objects start from and exactly how the three objects start to move. For any arbitrary system, such as moon around planet around sun, we can't calculate it analytically from first principles. The best we can do is run a simulation, run a numerical approximation. And what we tend to do is ignore anything that doesn't look like it matters. If we're trying to work out how does the moon go around the Earth, we temporarily ignore Jupiter and Saturn and Uranus and Neptune and Mercury and Venus. And we just put those in as little corrections afterwards. Ignore what doesn't matter and then make corrections. That's the only way we can deal with this sort of problem. And that's true when we're trying to get from one planet to another. We make approximations, we run simulations, and we make corrections for the extra tug of Jupiter and the tug of the Sun and the tug of Saturn and the tug of everything else in the solar system. So let's see how we go, for instance, from Earth to Mars. Here in 2018, we're leaving Earth. There's Earth's orbit in blue, and we're heading to Mars, and there's the Mars orbit in green. We're leaving Earth down here. We are the purple object here, the purple blob. We're leaving Earth. Notice that we left Earth when it was down here, and we don't arrive in Mars until we're on the other side of the solar system. That seems like a very inefficient way of getting there, but actually that's the most fuel efficient way of getting there, when Earth is on one side of the solar system and Mars is on the other. Let me just run that simulation again. Notice that we are leaving Earth. We're going a little bit faster than the Earth. When we eventually get close to Mars, notice that we're actually going more slowly than Mars. Mars is behind us and catching us up. So actually, Mars is going faster than we are at that point. If we want to rendezvous with Mars, we've got to accelerate at that point and go a little bit faster. Now, that is way too much information and getting very close to maths, so let's get rid of that and just think about the basics of, well, we're going from one planet, there's the green planet Earth, and we're heading for the red planet Mars. Quite definitely not to scale, even if you ignore the fact that this is squashed somewhat. We've made the Mars orbit rather bigger to make it easier to see what's going on. If we want to get from Earth to Mars, we leave Earth when it's at one point in the solar system, and we arrive at Mars on the opposite side of the Sun. So actually we follow the orbit there, the blue, the light blue orbit, which is called a Hohmann transfer. It's a way of getting from the Earth to Mars with the least amount of effort. It's actually an elliptical orbit around the Sun, such that the closest distance to the Sun is the same as the Earth-Sun distance, and the most remote distance from the orbit to the Sun is the same as the Mars-Sun distance. So we can coast from one to the other. If we leave Earth, we need to fire our rockets to increase our velocity. All of orbital mechanics is about velocity and velocity changes. It doesn't actually matter what the acceleration is. What matters is I want to increase my velocity. It doesn't matter whether you do it in 1 second or 10 seconds or 100 seconds. What matters is I need to increase my velocity by a certain amount. In the case of getting to Mars, it's about 3 kilometers per second. That's the increase in velocity you need compared to the velocity of Earth around the Sun. If you increase your velocity by 3 kilometers per second, then you'll end up on the blue transfer orbit, the Hohmann transfer. Remember, we need a kick to get onto the blue, but when we reach Mars, remember the previous animation, when we get to Mars, Mars is going faster than we are. So if we want to rendezvous with Mars, we need another kick to accelerate about 2 kilometers a second in this case, in order to get to the same speed as Mars. And that, because we're not using any rocket fuel as we're coasting from one to the other, is the most fuel efficient way of doing it. A kick to leave Earth, a kick to arrive at Mars, coast for the remaining 8 or 9 months, which is roughly how long it takes to go from Earth to Mars. When you look at that, you think, well, that's actually quite handy because if we follow the blue line to get to Mars, if we decide we don't want to land because something has gone wrong, all we have to do is not give ourselves that kick and we'll continue on the blue line because that's an orbit around the Sun. So if we decide not to land on Mars, we don't give ourselves a rocket burn at that point, we'll continue to follow the blue line back to Earth's orbit. Great. Except Earth takes a year to go around the sun. Mars takes roughly 2 years to go around the sun. The blue orbit is in between the two. It's about 1.5 years. In other words, 8 or 9 months to get there, 8 or 9 months to get back again. So yes, if you follow the blue line and don't give yourself a kick to land on Mars, you do indeed come back to the point where you left. But you come back 1.5 years later. Where's the Earth after 1.5 years? It's done 1 loop and half a loop, so the Earth is now on the other side of the sun. You come back to the Earth orbit, but Earth isn't there anymore. That's one of the problems with going to Mars. It is not a simple thing to do. You've got to worry about where is Earth, where is Mars, and you can't simply come back as fast as you went. You effectively have to stay on Mars for quite a few months before Earth and Mars are in the right positions to come back again. That's why missions to Mars last something like 2 years. It takes 2 weeks to go to the moon and back, but it takes 2 years to go to Mars and back because of this problem with planetary alignment. What about getting to other planets in the solar system other than Mars? Well, in the 1960s, it was realized that if you want to do it the really cheap way, if you want to minimize the amount of fuel you're going to use, you can use gravity assists or slingshots or flybys if you prefer. NASA tends to call them gravity assists. You can use the gravity of planets to help you along the way and give you a speed boost and send you on the right direction to go from one planet to another to another. That means you can explore, for instance, planets in the outer solar system. You can do it faster because you get a speed boost as you go past a planet, and you can do it cheaper. Cheaper because if you don't have to fire your rocket engines, if you use the gravity of a planet rather than your rocket, you can take less fuel, or if you prefer, more scientific equipment. So you can do it more cheaply because you don't have to have as much fuel, you don't have to have as big a rocket as you would otherwise need. So how does this work, this idea of a gravity assist? In a sense, the spacecraft takes some of the energy or some of the momentum from the planet. But if you think of basic physics, you start to question how that works. Because if we think for a moment what would happen if we had, for instance, a ball rolling down a hill, if we imagine we have a valley there and a ball sitting on top of the hill, then when the ball rolls down the slope, a physicist would say you're losing potential energy and trading that off by gaining kinetic energy. But everybody knows when you roll downhill, it goes faster. Everybody knows that. And the maximum speed will be when you're on the bottom of the valley. Like all good physicists, I'm going to ignore friction and I'm going to ignore air resistance. This is just a perfectly smooth roller coaster from a hill to a valley to a hill again. So as it falls down the hill, or as it rolls down the hill, it gains speed. It has maximum speed down the bottom, and when it comes up the other side, it will start to lose that speed again. If you end up with a hill on the other side the same height, you'll end up back at a standstill at the other end there. One of the physics principles is, because of conservation of energy, whatever you lose in terms of potential energy, you gain in terms of kinetic energy. That means the speed on the way down and the speed on the way up must be the same at any given height. I can put that grey line anywhere, and the speed on the way down will be the same as the speed on the way up. Amazingly, it doesn't even matter what the shape of the hill is. As long as it's frictionless, as long as we ignore that, if we're rolling down a hill and rolling up a hill, one hill can be bumpy, the other hill can be straight, one hill can be a high gradient, the other can be a low gradient. It doesn't matter. When you reach the same height, you must be going at the same speed because of the conservation of energy. So when you say that, then you ask, well, how does flying past Jupiter give you a speed boost? If going down a hill gains speed and going up a hill loses speed, why is it different for Jupiter? So let's think about what happens there. We're flying past Jupiter. The maximum speed, the equivalent of the bottom of the valley, would be the maximum flyby speed when we're closest to Jupiter. And there'll be some speed on the way in and some speed on the way out. But from what I've just said, you'd think, well, surely whatever you gain by falling towards Jupiter, because Jupiter is pulling on you, in a sense, if you prefer that, we're falling into Jupiter's gravity well. Whatever we gain on the way in, surely aren't we just going to lose it on the way out? Surely those two speeds are going to be the same when we are at some arbitrary large distance from Jupiter. Well, yes, but here's the clever bit that they figured out. The speed on the way in and the speed on the way out are the same as seen by Jupiter. In other words, if we imagine ourselves on Jupiter, we will see a spacecraft come in and we will see a spacecraft go out at the same speed, at the same distance. But Jupiter is not stationary. Jupiter is going around the sun at some speed. So if we arrange it so that we come in broadside to Jupiter's motion and we leave in the same direction as Jupiter's motion, our speed will be the same relative to Jupiter, but if we leave in the same direction as Jupiter, we're effectively adding our speed to its. We gain a boost because we're now traveling in the same direction that Jupiter is traveling. And as seen by Jupiter, we're at the same speed, but now, after coming in broadside and leaving in the same direction, we get a speed increase. Speed relative to Jupiter is the same, but the speed relative to the Sun can be considerably different. If we arrange it right, we might be coming in at 10 kilometers a second, but we can leave Jupiter's environment at something more like 25 kilometers per second. The speed increase can be significant. And if we change the geometry, instead of leaving in the same direction, if we left in the opposite direction, we would slow down rather than speed up. But for the outer solar system, this is what we want. We want to get a speed boost so that we can go visiting the outer planets. In the early 70s, this was put to the test. It was calculated in the 1960s that this ought to work. It was put to the test in the 1970s. Firstly, Pioneer 10. We leave Jupiter. Look at what happens when the purple meets Jupiter. Bam! A sudden speed increase and a dogleg turn to the left. It's now moving in the same direction as Jupiter and it gets an enormous speed boost as it leaves the environment of Jupiter. Pioneer 11, same sort of thing. This time we're going to pass Jupiter and we're going to try and arrange it so that speed boost that we get from Jupiter is going to send us on to Saturn. So we go to Jupiter and not only do we get a dogleg and a change of velocity, it actually sends us to the other side of the solar system where Saturn is waiting for us. The tick marks, by the way, are just showing that we are above the plane of Jupiter's orbit. It tells you whether it's high or low. So actually it got a kick here and went slightly high and arced over the top and then arrived at Saturn. Both Pioneer 10 and Pioneer 11 are leaving the solar system as a consequence of getting that speed boost. Pioneer 10 heading off towards Aldebaran, Pioneer 11 heading off towards the center of the galaxy. A few years later, that was tested again with Voyager 1. The original idea was we want to visit Jupiter, get some nice images of Jupiter and its moons, and also we want to go on to Saturn and get as close as we can to its rather interesting moon Titan. So Voyager 1 passed Jupiter, got a speed boost, and on its way to Saturn, it didn't attempt to get a speed boost because it wanted to go as close as possible to the moon Titan. And it did indeed do that. Titan's got a very thick atmosphere. It appears to be a rather large moon with an atmosphere. That makes it rather unusual. And it was definitely worth having a look at what's going on. Because Voyager 1 successfully went past Titan, there was no need for Voyager 2 to do the same. That was the backup insurance policy. If Voyager 1 failed, Voyager 2 would have gone past Titan to see what was going on. It was thought at this point, we've got enough information from Titan, we can do something more ambitious with Voyager 2. We can launch from Earth, we can get a speed boost from Jupiter, which will send us on to Saturn. Now we'll use the Saturn speed boost, another kink there, and we'll do again from Uranus and send us on to Neptune. When passing Neptune, they thought it'd be very nice to have a close look at its moon Triton. So they looked at Triton. They didn't attempt to get a speed boost from Neptune. There was no need. It's already going fast enough to leave the solar system. It went over the top North Pole of Neptune in order to get a good look at Triton on the other side. Notice the tick marks indicating that this Voyager spacecraft dived below the plane of the solar system. And Voyager 1 and Voyager 2, again, now heading out of the solar system. They are currently something like 150 astronomical units, 150 times the distance from the Earth to the Sun. If we think of what that speed looks like, if we go with, in this case, it's Voyager 2, so we've got 4 different gravity assists in principle. Here we're plotting the speed relative to the sun as a function of distance. Remember, 1 AU is Earth to sun. So we can see what happens if we start with the Earth. The speed drops originally because we're moving away from the sun. Then we get an enormous kick of speed from Jupiter, a big kick from Saturn, a big kick from Uranus. Notice that although we gain speed on the way into Neptune, we lose it all on the way out because this was not arranged to be a gravity assist. This was fall into Neptune's gravity well, come out of Neptune's gravity well in such a way that we get a close look at Triton. So the only one where the output velocity is lower than the input velocity is Neptune. In all other cases, we get a significant speed boost. Jupiter is a very massive planet, so that bump for Jupiter is obviously quite large. As soon as we've got that speed bump from Jupiter, if we want to leave the solar system, we don't need any more. Jupiter, being so massive, is large enough to give us a speed boost that will get us out of the solar system. If we were to plot the escape velocity from the solar system, that's the blue line, you see that we are not above the blue line until we get to Jupiter. As soon as we pass Jupiter, we're now above the blue line, and we stay above the blue line regardless of whether or not we get additional kicks from Saturn, Uranus, Neptune, etc. So from that point onwards, it was essentially inevitable that the Voyagers would leave the solar system. Well, gravity assists to get out there are reasonably intuitive. If you fly past Jupiter and you leave Jupiter in the same direction that Jupiter is moving, you're moving at a given velocity relative to Jupiter. So if you're moving in the same direction, you've got this speed boost. That means you can get to the outer solar system faster. You can get there in years instead of decades. You can save fuel. Fantastic. But it's not perhaps as obvious that we use gravity assists for the inner solar system as well. Bepi-Colombo, for instance, was launched in 2018, and it's been spending years doing gravity assists to try and slow down. If you simply drop a spacecraft into the middle of the solar system and allow it to fall towards the sun, it'll be going way too fast when it reaches Mercury. You want to slow down. So actually, Bepi-Colombo had flybys of the Earth, flybys of Venus, flybys of Venus, flybys of Mercury. And although it reached Mercury years ago, it still hasn't gone into orbit around Mercury because it's still trying to bleed off speed. And it does that by continuous gravity assists by encountering other planets. So a flyby is only a question of geometry. If you leave in the same direction as a planet, you gain speed. If you leave the planet in the opposite direction, you lose speed. It doesn't matter whether you're gaining or losing. The bottom line is, regardless of whether you're accelerating or decelerating, you can do a maneuver that saves fuel. You're using the planet. You're not using your rocket engines. You're not using fuel to change your velocity. And hence, you can get to where you want to be, whether it be the outer solar system or the inner solar system, by using the momentum of the planets themselves rather than firing your rocket engines. You can take more scientific gear if you have less fuel to worry about and smaller rockets. So Bepi-Colombo will be going into orbit finally around Mercury, despite being launched in 2018 and thinking, well, it's not that far to Mercury compared to Pluto, and yet it's taken 8 years before it can go into orbit. Bepi-Colombo should be in orbit around Mercury sometime towards the end of this year. I think November 2026 is the current plan. So gravity assists, fantastic idea for getting around the solar system with the minimum amount of effort. It was figured out in the 1960s. Effectively, we've been using it ever since. If you want to change your orbit when you get to wherever you're going, for instance, Cassini went to Saturn, and between 2004 and 2017, it kept changing its orbit because it went into orbit around Saturn, but it wanted to have a close look at the planet. It wanted to have a close look at the rings. It wanted to have a close look at all the interesting moons that are around Saturn. So it continuously changed its, not continuously, every once in a while it kept jumping from one orbit to another in order to investigate an interesting moon, an interesting angle on the rings or whatever. And of course, that needs fuel. If you want to keep changing your orbit around a planet, you need fuel. So that ultimately determined the mission lifetime of Cassini before it was finally crashed into Saturn in 2017. You can see how complex the overall structures of the orbits were there. So we thought about different orbits. We thought about how we go from one part of the solar system to another. But what's this we hear about Lagrange points, where you can park a spacecraft and it just sits there doing nothing? If everything is in orbit around the sun, what do we mean by a parking place? How can you park Gaia or the James Webb Space Telescope or solar telescopes, for instance, in the solar system and expect them to stay put? We come back to this idea because it's absolutely central to Lagrange points. Let's remind ourselves again, if we've got two hypothetical planets, the one closer to the sun feels a stronger gravitational force, so it moves faster and has a shorter orbital period, a shorter year, if you prefer, compared to the outer planet, which has a weaker gravitational pull and hence a longer period to go round the sun. Okay, if we think about the forces on the two objects, let's for the moment think about Earth and Mars, for instance. Earth is being pulled towards the sun with a strong gravitational force. Mars is being pulled towards the sun with a somewhat weaker gravitational force. The greater the distance, the lower the force. 1 over r squared, as Newton told us. Is that always the case? Well, yes, it's always the case that the distance from the sun will determine the gravitational pull of the sun, but it is actually possible to change the geometry. We can't change how much the sun pulls on the green planet or the red planet or the green object or the red object, but we can engineer things such that an object, for instance, an object in the red orbit, feels a force other than just the force of attraction of the sun. So let's imagine that these two objects now, green is the Earth. Let's imagine red is not necessarily Mars. Red is simply the orbit of something orbiting with a radius, an orbital radius greater than the orbit of the Earth. So the red is an object that we are interested in. It could be a spacecraft, it could be a space telescope, for instance. So Earth, of course, goes around the sun in 1 year. The red orbit, if red is further away from the sun, it has a period, it has a year of more than 1 year. So red will go round the sun in a time scale greater than 1 year. But what if we could arrange it that the red orbit is close enough to the Earth that it not only gets pulled by the sun, but there's an additional force on the red object, i.e. the force of gravity produced by the Earth. What if we can arrange it so that the red object is pulled by the sun and the Earth? We can calculate, we're not going to do the maths, but we could calculate where do we have to be such that the pull of the sun and the pull of the Earth combined on the red object make the red object go round the sun in 1 year. Remember, without the pull of the Earth, it'll take more than a year. It's going more slowly. But with an additional pull, a stronger gravity, it'll go around faster. Instead of taking more than a year, it will take a year. We can find what orbit will allow that to happen, so the red object now goes round with the Earth. Both the Earth and the red object are going to go round the sun in 1 year. Completely different from what we had before. They are now in sync. The red object is always on the opposite side of the Earth to the sun. Sun, Earth, red object, straight line, always a straight line, compared to what we had before, where the inner planets move faster than the outer planets. Let me run that animation one more time. Because we have the additional gravity pulling on the red object, Earth and sun, they go round in sync. They go round together. And that is the basic concept of Lagrange points. Because if we think of the red object going around with the green object, let's take away all the extraneous stuff and just leave ourselves with the Earth goes around the sun. The object we're talking about is basically the Lagrange point. It happens to be Lagrange point number 2. Lagrange point number 2 is being pulled not only by the sun, it's being pulled by the Earth, and the combination of those two allows it to go round the sun at the same rate as the Earth, 1 revolution in 1 year. I have not attempted to make these cartoons to scale. The distance from the Earth to the Sun is 1 astronomical unit, and the distance between the Earth and Lagrange point number 2 is about 1% of that, so it's 0.01. It's about 1 million miles, roughly speaking, or 1.5 million kilometers. So again, quite definitely not to scale. The idea, the concept, is the same for any of Lagrange points. So for Lagrange point 1, that's a point in between the Sun and the Earth. So now we have, for Lagrange point 1, the Sun is pulling one way, Earth is pulling in the opposite direction, which means the total gravitational pull on L1 is less than simply the Sun on its own. So instead of L1 going around the Sun quite quickly, because it's closer to the Sun, the Earth is pulling it back and allowing L1 to go round 1 revolution in 1 year. So L1 goes round with the Earth as well. A great place to park a solar telescope. The same non-scale applies. If we've got 1 AU as the distance from the Earth to the Sun, the distance from L1 to Earth again is about 0.01. It's not quite the same as the distance to L2, but it's close enough. It's 1% of an astronomical unit. And it's a great place to put a solar telescope because you have an uninterrupted view of the Sun. The Earth is behind you. The Earth never gets in the way of your view of the Sun if you're sitting at L1. It goes round with the Earth, and L1 is always between the Earth and the Sun. So yes, there are solar observatories there. There's also a plan to put NEO Surveyor, the Near Earth Object Surveyor, looking for asteroids. A lot of asteroids we miss because they go around the Sun and we don't see them because of the glare of the Sun until they hit the Earth. Well, the dinosaurs didn't see it coming, did they? So it is always possible that that's what will happen. So as well as having telescopes looking out onto the night side of the Earth, the intention is to have a near-Earth object surveyor at L1 looking for any objects that are coming round from behind the Sun to give us advance notice of any rocks, comets or asteroids that might be coming our way. We can calculate where these Lagrange points are. Remember, it's only a question of saying the additional pull of the Earth will give us a period of 1 year. So it's only a question of applying Newton's law of gravitation. We know that gravitational forces fall off as the square of the distance. The gravitational pull between any two objects depends on the mass of those objects and the square of the distance between them. When you throw all that into a calculation of Lagrange points, that's all there is to it. There's m is the masses, r is the distances. All you have to do is to solve that equation. Shall I give you a second to do that in your heads? No? Okay, so yeah, all we have to do is to solve for r, and then we have the distance to the Lagrange points. Yes, I know my splash screen said it's not that hard if you just skip the maths, so yeah, okay, we'll skip the maths. The point is, it can be done. It's the sort of thing we ask undergraduates to calculate. It can be done as a point of mathematics. It's only force depends on 1 over r squared. Put it into the equation, shuffle it around, get an answer, and the answer comes out to be the distances I've indicated. Turns out there are 5 Lagrange points. They were originally discovered by the mathematician Euler, but then along came Lagrange, who found another 2 and said, I want to name them after me, or at least posterity has named them after him. So there's L1 that I started with, L2 that I started with, L1 between the Earth and the Sun. There's actually a counter-Earth, if you want to think of it that way, a point on the opposite side of the Sun from the Earth. That is a Lagrange point as well. 4 and 5 are not so obvious, because when you think of 4 and 5, the Sun is pulling one way and the Earth is pulling a different way. It's not like they're pulling in the same direction. It's not like they're pulling in opposite directions. Earth is pulling this way, Sun is pulling that way, exactly 60 degrees apart. It is not initially obvious why it is that when Sun pulls one way and Earth pulls another way, you get another Lagrange point. But then Euler and Lagrange were quite clever mathematicians. They worked it out. We're not going to go through the maths. Each of these red dots is a point where, in principle, you can place an object and it will stay there relative to the Earth and Sun. Remember, that doesn't mean it's not moving. It means as the Earth goes round the Sun, all of these red dots go round with the Earth. All of the red dots appear stationary as seen from the Earth relative to the sun. If the sun is over there, these red dots will stay in the sky. L2 is always sitting above midnight. Noon on the Earth is, of course, facing the sun. Midnight on the Earth is this side of the Earth, and L2 is always hovering 1 million miles above midnight, regardless of anything else. And that, of course, is a very good place to put spacecraft. For instance, you can put Gaia there, which relatively recently, Gaia has moved away from L2. But for over 10 years, Gaia was at L2. If you have a sun shield there, you can shield yourself from the sun and the Earth and the moon all at the same time, because they're all in the same part of sky. So in effect, you can observe deep sky over here, knowing that everything else that you're worried about, the heat of the sun, the heat of the Earth, the heat of the moon, are always on this side, and one heat shield will keep everything out of your precious instrumentation. So a sun shield can block the light from essentially everything else that you're worried about. Well, actually, if you think about the distances involved, L2 is about 1 million miles from the Earth. That's about 4 times longer than the distance from the Earth to the moon. And we know that the shadow of the moon just touches the Earth. That's why we get a total eclipse every once in a while. Earth is 4 times bigger. L2 is 4 times further away. That means Earth's shadow just touches L2 in much the same way that the moon's shadow just touches the surface of the Earth. So if you actually sit at L2, you're just at the point of eclipsing the sun. And if you've got solar panels on the back of your heat shield, your sun shield, you want to charge those up. Being in an eclipse state is not a good idea. So nothing actually sits at L2, both for the reasons that you want to charge your batteries, and also because you might want to put more than one spacecraft there and you don't want them banging into each other. So you don't actually place an object at L2, you put it in a little so-called halo orbit, as shown by this little golden circle there, seen edge on. It's called a halo orbit because it's orbiting this way, not orbiting in the plane of the projection screen, but orbiting out of the projection screen, hence the halo orbit. Any spacecraft that's orbiting around this red dot, if it moves upwards in the sense of towards the ceiling in this room, it'll get pulled back downwards by the Earth. If it goes downwards, it'll get pulled back upwards by the Earth. In other words, there's a sort of self-restoring force this way and that way. But if we think about motion towards or away from the Earth, that's different. If a spacecraft around L2 drifts towards the Earth will pull it in even faster. If it drifts away from the Earth, it'll drift away even faster. So the behavior in the plane of this wall, left-right, is not the same as the behavior up-down. We can represent what's going on there by thinking about this rather peculiar and rather colourful donut. The ability of any spacecraft to park at the Lagrange points, and we're going to concentrate on L2 here, can sometimes be visualized by this donut with a whole load of contours that have been drawn on it. And we can imagine these contours are, if you like, height above sea level, and ask ourselves, if we placed a little ball bearing on this, would it roll downhill? Which way is downhill according to these contours? So if we think about the contours representing height and think about which way is downhill, we can look more closely around L2 to see what's actually going on for spacecraft like Gaia or the James Webb Space Telescope. So let's zoom in there. Red contours are high, blue contours are low. Let's zoom in and see what that actually looks like. There's the Earth, there's L2, and we've got high contours and low contours, red and blue respectively. The arrows show the direction of downhill. If you look at it, if we're going from red to blue, that's downhill. If we are here, that way is downhill, and that way is downhill. So L2 is not a hilltop. It's not downhill in all directions. That's what a hilltop would be. And it's not a valley or a well, because that way all of the arrows would point towards the L2 point. 2 arrows point towards it, 2 arrows point away from it. So it's not a hilltop and it's not a well. What shape is neither a hilltop nor a well? Well, it's a saddle point, or at least mathematicians call it a saddle point. In 2 directions you fall off the saddle, In the other two directions, you go up the saddle. Mathematicians call it a saddle point. Everybody else calls it a Pringle, because that is precisely what it is. This is a genuine Pringle, not a faux Pringle. It's not this sort of thing where some manufacturers will make these particular crisps and they won't put the correct curvature in. If it's a Pringle, it'll have the curvature which is different in the two directions. And that is where the James Webb Space Telescope is sitting. If that's the only take-home message from this, James Webb is on a Pringle. That's something you can remember. So again, it's not actually sitting at L2, it's doing a little so-called halo orbit around L2, as was Gaia until Gaia was retired a few months ago. It'll need a little bit of station keeping because it's quite happily orbiting around this point, but it will very slowly drift towards Earth. If you don't get it precisely at L2, it'll drift towards Earth. And every once in a while, they give it a nudge. They've got some jets on board just to give it a nudge to push it back towards L2. What they do not want to do is to go beyond L2. If it ever got beyond L2, they would not be able to push it back again because the jets are on this side of the sun shield. Everything on this side of the sun shield has to be kept really cold because it's an infrared telescope. So there are no jets on this side to push it back again if it ever drifted too far. So they allow it deliberately to drift towards Earth and give it a nudge, a very careful nudge towards L2. They never want to give it such a hard nudge that they push it over the top of the saddle and out the other side, because then it effectively would be lost. Or they'd have to turn it around and push it back again with those jets, but then the precious telescope would be pointing towards the sun, and everything they'd done up till now to cool it all down would be lost because it would all heat up again. And it would take them months, if not years, to get back to square one. So it's very important that they get it to the correct place and they station keep it by giving it a little nudge of their jets every once in a while. The precision with which JWST was placed at L2 was so good. They reckoned that the fuel, which hopefully would have lasted 5 years, they used so little fuel to get it to L2, they reckon the fuel will probably last not 5 years, but probably more than 10 years. And so they'll be able to station keep for a long, long time, far longer than they had first feared might be the only lifetime of the JWST. So they might have doubled its lifetime simply by the precision with which they could place it in that location. Some orbits look really, really weird. For instance, there are some orbits that look like that, so-called horseshoe orbits. The arrows show you how an object moves. At first sight, you think that's ridiculous. But if you follow the arrows, you realize, well, actually, they still obey the rules. When closer to the sun, it's going faster than the Earth, so it catches up the Earth. But as it catches up the Earth, it gets pulled by the Earth to a point outside the Earth's orbit, which means it's now going slower than the Earth, which means it then follows the outer part of the horseshoe, and then round and round and round it goes. So it does obey the rules. Closer to the sun moves faster, further than the sun moves slower. And although we don't necessarily see objects going around Earth's orbit like this, we do see this for certain moons. When we look at the moons of Saturn, for instance, we do see some moons that appear to be in these horseshoe orbits. But perhaps the weirdest orbits of all are the orbits that are not circular, not elliptical, not parabolic. If we started with 3 stationary objects and said, let's just place them there carefully, and then let go and ask ourselves what would happen, we can calculate how these 3 objects would move. And the answer is not what you expect. Here's a simulation. The objects don't go into orbit around each other. They go and then they stop and then they fall backwards again and retrace their steps exactly, like a roller coaster. So orbits do not have to be closed. The ones we're used to, planets going around stars, they are closed orbits. Could we ever envisage this actually happening? Well, not really, because you have to start with a very precise set of objects at a known position, at a known velocity, possibly not moving at all. And that's very unlikely to occur naturally. And don't get me started on black holes, because what's going on around black holes, space is so distorted then the laws of Kepler and the laws of Newton just go out of the window completely, and we end up with something that doesn't appear to be an orbit at all. It appears to be chaotic. So, to conclude, why is rocket science considered to be so hard? Why do we say if something sounds hard, wow, that sounds as difficult as rocket science? Well, we believe rocket science is hard because it is somewhat non-intuitive most of the time. Yes, there are objects in the solar system that move in ways that are, at first sight, weird. Nobody would have thought a horseshoe orbit is a sensible way for an object to move in the solar system. And yes, putting the James Webb Space Telescope in exactly the right place around L2 in order that it stays put in a particular patch of sky, orbiting a point in the sky with such amazing precision, that was not an easy thing to do. And that was a difficult thing to calculate, and it was rather expertly executed. However, I argue that the underlying principles are straightforward enough. Strong gravity leads to fast motion. We know that, for instance, Earth goes around the sun faster than Mars goes around the sun. And this idea that stronger gravitational pull leads to faster motion, I would argue, underpins everything in orbital mechanics. That's all there is to it. The rest is just mathematics. After all, it's not rocket science. Thank you all very much.